Hi, in this video, we want to look at some ways to pre-process our data for structural equation modeling. Okay, so we're in the situation that I want to do either factor analysis or I want to do structural equation modeling. Now, if you think about those depend completely, totally, and utterly on linear algebra from the whole principal component analysis aspect. Okay, so that's fine, dandy, as long as our variables have linear structure between them. So if they have a linear structure, linear relationships, approximately speaking, it doesn't have to be perfect, but approximately, then everything's fine and dandy, everything's great. I'm happy, I run my model, and then I proceed to analyzing my model. Now, what about the situation where it isn't a linear relationship? What if we're talking about the case where, well, it's there is like a increasing or decreasing relationship between the variables, but now when I say increasing, decreasing, I mean statistically. So there is an increasing or decreasing relationship, but it's not linear. All right, well, what's going to end up happening is I'm not going to get really a model that represents what's going on as well as it should. All right, because there is a relationship. There's an increasing or decreasing relationship statistically, but I'm using a model structure, a geometric structure that only handles linear aspects. Okay, so I'm going to have a shortcoming in my model. Well, how can I deal with it? What can I do? All right, so the data that we're going to go over, the examples we're going to look at, are modified from modern psychometrics with R by Mayer. Here's the GitHub page to get the code I base this off of. And it's a really good book. Check it out. All right, so let's say that I've got, Likert data, I've got ordinal data, something like that, and I want to run it. All right, so how I see it, we have three major options in this situation. First one, I call this the turning a blind eye method. I just pretend it's numeric and run it as is. It's probably the most common one in actual practice. Now, and something that's good about that is that, I don't have to justify my data prep step. Okay, so if I need to get under, if I need to start talking to people about my model and what I did, but they don't understand the whole linear aspect of principal component analysis or factor analysis, then this is a good option. Now, everybody who knows the difference between ordinal data and numeric data, who really understands it, is going to have a conniption over this, and they're going to throw a tantrum, and you'll have problems. All right, so we need another option. Well, we could go with Polycore Correlations. The problem with that is that not all functions accept correlation matrices when we're doing this type of work. All right, so if a correlation matrix is not enough, that it actually wants the original data, giving it a Polycore correlation isn't going to solve the problem. I need data, data. I cannot make bricks without clay. So what we're going to do, we're going to look at another option, and this is the focus of the video, is to transform the data to linearize it. All right, so what we're going to do, we're going to drop our data, our ordinal data, into a function that is going to do its best to figure out a good way of transforming the data into linear data. Now, there's going to be several different ways, and it's based off of different maximization or minimization criteria. Okay, so first and foremost, let's load the data. And here we're going to go with some data about skiers who are going out of bounds on the data set. So this is like brief short-term sensory questionnaire. And this is, assessing someone's desire to have an exciting experience. And all the subjects in this study were skiers that were out of bounds in some area. Okay, and so I've got the data. Let's go ahead and just visualize it real quick, just so we can get a feel for what's going on. And so I'm going to use ggplot. ggplot, I want tidy data, which is a long format compared to what I have. And so I'm going to go ahead and do just a regular old bar plot. And so we can see that the fields that we have are bungee jumping. How much do they want to do bungee jumping? How much do they like to explore new areas without really knowing what they're going into? How much do they like exciting and unpredictable friends? How much do they want to experience frightening experiences? How much do they want to experience something, even if it's illegal? How much do they like wild parties? How restless do they get when they're at home? And how much do they like going on trips without like a plan or a schedule? Okay, so we can see the data and we can see the distributions. Keep this bar plot in your mind for later in the video. All right, so what we're going to do, I'm going to go through, I'm going to transform the data in multiple ways, and then I'm going to run structural equation modeling on each of the transformed data, and I'm going to pick the one that gives me the best results for the model. Okay, so what I'm going to do, I'm going to store all my transformed data in a list. I'm going to call it list underscore data. And the first one is just the untransformed data. That way I have that as a baseline to compare the other transformations. Okay, so now let's go ahead and let's grab the aspect package. What we're going to do, we're going to take the different ways that it gives us tools to transform our data, and then we're going to take the transformed version of it. All right, so there's several different options that we have when it comes to the optimization on the transformation. And so what this does, this function here, the core aspect function in the aspect package, what it does a transformation on the data. It looks at it and it's working to optimize the correlation matrix in some manner. Okay, so transform the data, take correlation matrix, look to see what the what the optimization result is. All right, so first one is to take the sum of absolute values of the correlations to some particular power. Next one is the sum of correlations to a particular power. Then there is we're trying to maximize the determinant of the correlation matrix. Then we want to get the sum of the first p eigenvalues. So there's a direct relationship between the determinant and the eigenvalues. Here we're only working with the first p, so there is going to be a little bit of a difference there as long as I'm not using all eigenvalues. Now we're going to take the square multiple correlations, and this one is sum of all squared multiple correlations. All right, this is good for path analysis. Now, here is a vector of all of our options, except I removed aspect SMC. And so here, the squared multiple correlations with respect to a target variable. I couldn't come up with a good target variable for the video, so I just excluded it. I didn't want to add it in, make it more complicated. And so what I'm going to do, I'm going to take the core aspect function in the aspect package. I'm going to drop in my data. I'm going to tell it which aspect I want to be optimized, and then I'm going to just tell it its ordinal data. Now, after it does the optimization, I'm going to grab the score matrix. So this is our transformed data, and then I store that data in our list. Okay. So at this point, our list of data has 1, 2, 3, 4, 5, plus original, 6 data sets in it. All right, so now let's go ahead and use another function in the aspect package. Let's talk about Lineals. All right, so Lineals, what they do, they work to achieve the best transformation for bivariate regression across the entire data set. And so this is very good for factor analysis. So what we're trying to do, we're trying to get the best 2-variable regression results we can from our data set. And we want the best linear transformation that achieves this. All right, so I just take the Lineals function from the aspect package, drop in my data. I tell it I'm using ordinal data, and then I'm grabbing the score matrix. Now, if I want to work with the lineal, much like I do with princows or hamals, I can work with the entire output. But for this one, since my goal for this video is to do a structural equation modeling, I'm really focused mainly on the output of the data prep, not the actual data prep itself. All right, so now let's go ahead and go through for each of my transformed data sets. I'm going to fit the same model, and whichever data gives me the best model, that's the version of that is the transformation I'm interested in, that I want to keep. Okay, so I'm going to specify my model equation. And so we're going to say ES is explore and trip. All right, so exploring unknown areas, going on trips without a structured plan. BS is restlessness and friends. TAS is frightening and bungee jumping. DIS is wild parties and willingness to do illegal things that are exciting. And then overall risk is the sum of all four. Okay, and what I'm going to do, I'm going to, each time I fit a model, I'm going to store it in a list. That way I can iterate over the list to work with it in a moment. Okay, so now I'm going to do a confirmatory factor analysis with the Lavon package. Each time I'm using the same model. We're using weighted least squares. This is what the author did in the textbook. And the optimization method is pretty standard. We're not going to check the gradient because like we just want to run through things as quickly as possible. And then after I get the model that I select, I'll worry about the gradient later. So here I'm just running through all my models. I want to be quick. I want to identify the one that's the best fit, and then I start digging into my model deeper. So I'm not going to worry about the gradients. And I have ordered data. Okay, and so I'm iterating over all of my prepared data. Now what I do at this point in the code, I have several. I have what, 7? I have 7 different models. All of them are the same equation from the one that I specified earlier. The difference is my data prep. Everything about my models are the same, except for the difference in how I prepared my data. Okay, so let's go ahead and get the root mean squared error of all of my models. So what I'm going to do, I'm going to use the sapply function. I'm going to put each confirmatory factor analysis model in it. I'm going to use the fit measures package to get the statistics out, and I'm only interested in root mean squared average. All right, so this sapply statement gives me the root mean squared error of each model, and now I'm going to go through and I'm just going to sort it just so I can see how they shape up, how they compare to each other. All right, so we can see that the one that was the smallest was the lineal. All right, so that that looks like the way that we're going to want to go. Well, now let's take a look at the rest. All right, with no data prep at all, I have 0.132, and I notice I have 0.132 for all the others. All right, so this shows me that the other ones are not really that great of a data prep method for this model, for this data set. It's important. So future situations, I might be able to get something better off of these. It might, maybe if I would change the parameters like the number, like the P, or change the power on the aspect correlations, then I may have gotten something better. But at first run, there's kind of a bit of a difference between these proportionately. So I think I'm just going to go with the lineal. And now at this point, I would start digging in deeper into my model. All right, well, let's go ahead and take a look at how our data was actually transformed. So what I'm going to do, I'm going to grab the data set that gave me the best model. And so here, just to make it automated in the code, I told it to just grab the one that grab the minimum of the root mean squared errors, grab that data set. So I'm using which.min to find where is the minimum. Then I grab the corresponding data set. I tidy up my data so I can use ggplot, and then I do my bar plot. Okay, so I was really surprised by this. I did not expect this result to come out. So when we look at the Lineals transform on our data, we can see that almost all of them convert into binary. So remember that we had 5 levels of each variable initially. Now that we look at the transformed version, and this was the best transformation we could find, we can see all but one has 2 levels. So friends got converted from 5 down to 3. The rest went from 5 down to 2. So we converted them into binary. So that is surprising. I did not expect this result. All right. So, next thing I would want to do, maybe look a little bit deeper, look at the data transformation, start looking at that model that I have and start analyzing like I would. And I would proceed forward. In most aspects, I would just pretend like it's the original data and treat it this way and move forward. But and present my results to my stakeholders, my decision makers, with what I've got. Well, that's all I've got for you. Take care and goodbye.